Hello everyone. I would like to present my linear algebra final project called PCA for face recognition. The problem I would like to solve is identification of the test face image among the faces in the storage. Solution to this problem could be an application of PCA algorithm to compare the new faces with existing. Imagine you have the machine that travels through the other planet and taking the photos. And then we need to transfer these photos to Earth. The size of these photos could be very big. And that is why we need somehow to compress each of them in order to transfer less data because of the bad connection between the planets. As far as images are represented as a tensors or matrix, we could apply linear algebra to reduce dimensionality of these images, which means transfer the images from space with some number of dimensions to smaller one which has less number of dimensions. Thus, we could find the space where we will have enough data, which means we won't lose important data, but we will reduce the size of the image significantly. It turns out principal component analysis, or PCA, is actually a dimensionality reduction algorithm, and it could be used for these kind of tasks. The main idea of PCA is the usage of orthogonal transformation to convert a set of observations, which could be possibly correlated, into a set of values of linearly uncorrelated variables, which is called principal components. The input data for the task is the set of images containing faces for training and the set of images containing different creatures. The first step of solution is calculation of mean face in the dataset. Then we need to subtract it from each image, and then we need to convert image matrices to vectors. The next step of our solution is creation of covariance matrix of dataset. Then we need to extract the eigenvalues and eigenvectors from it, and each of the eigenvectors will represent the variance in different dimension. Then we need to sort the eigenvalues in descending order. Thus, the eigenvalues with bigger value will be on the start of the array, and the corresponding vectors to these eigenvalues will contain the most variance. By multiplying the centered image vectors on the eigenvectors, we will obtain so-called eigenfaces. And now we could represent each image in the dataset as the weighted sum of the eigenfaces. The more eigenfaces are being used, the more accurate recreated image would be. As far as the eigenfaces are sorted in descending order, we could see that each of them contains different number of variants, and on the left plot we could see that with 138 principal components, the 95th of total variance could be represented. By using 349 components, almost 99% of dataset variance could be represented. On the plot on the right, we could see what part of total variance contains in each principal component. What if we get an unknown image? In order to deal with it, we need to move it to the eigenspace, thus performing dimensionality reduction. We could restore any image to some extent, but on the faces, restoration performs better. It turns out we could measure the performance of restoration even visually. We could take some number of principal components and see how the picture is restored. On the 100 of principal components, we can differentiate the actual image, and the quality improves with the increase of components number. We could restore any image, but on the faces the restoration performs better. As you can see, the mean squared error on the face restoration is approximately 10, while on the restoration of dog image is approximately 100. Restoration works with different accuracy for faces and non-faces. So we could find the threshold which we will use to differentiate two classes of images. Occasionally, we could find the best number of principal components where the separation of two classes is the best. The threshold is half of the distance between any two images in the dataset, and where the line of the threshold crossing the average error between two classes, that is the number of components to use. So now we can see the result of the solution. We separated the images containing the faces from the images containing other kinds of objects. As for face recognition, the approach is: if minimal difference between unknown and known images is less than threshold, then we could state that this image is in storage. Otherwise, this image could be a face or not. For face recognition task, I use another dataset containing 40 classes with 10 images in each. After performing cross-validation, I got 75% accuracy rate. Thank you for watching this video. You can find the link below to see this project on GitHub.